everyone. With this video, I'm going to show how to compute inverse modulo of a number um, with modulus n. And we already showed a algorithm just from the direct definition of inverse. So in that video, I have this. So what to be found that equal and 1, that's a remainder, plus some constant k times the modulo n, and divided by what's given 1 of the inverse, which inverse of which is to be found. Then what do? You find out, just try with different k, and then that's actually the quotient. And then you have, say, 1, then you see what you have. Then if you end up with an integer whole number, and then you're done. Okay, and then if not, if you have 2, and let's say 200.4, no. And then 3, and finally you get 4. And then once you have 4, and then you get 113, which is exactly integer. So then k equals 4. Then the d should be 113. So because that's the integer you find. Why is that true? Because then go back to the original definition, because this method is basically follow the original definition. Now see, if you have, say you find it, then 113, right, and 17, you multiply, and then this is 1 plus 4 times 480. So that's the k. And it's obviously this 113 is the inverse, because if you divide by 40, so the remainder is obviously 1. So if that cancels, so therefore, this is the method. This is called a brute force method. Brute force method. But in some cases, um, it's very slow, and I would not give you a very hard problem, but you keep on trying and you find out it's integer, that's the answer. And so that's the proof, that's the show, if you find the integer. But in some cases, the inverse doesn't exist. You keep going, you will never get the integer. And in that case, so this now in this video, actually, I'm showing you the standard algorithm called Euclidian and extended Euclidean algorithm. Okay, based on this concept. So you see, we find the solution of so-called Diophantine equation over here. And this is given a number, so A over here is given, and N is given here. Then, so we find the solution X and Y, which we find equal 1. Both X and Y are integers. X and Y are, once we find that integer solution and multiply, and then that is the inverse. Why is that? See, let's say you find out, in fact, this X is what is actually D here, and negative K is Y here. And then if you rewrite this into this, X equals 9Y, and then you see it matches exactly with what we define. Therefore, it can easily show that if you find a solution of this equation with integer x and y, not any integer x and y, and then you find the inverse, um, as I have proven here. So now, but does it have the integer solution? Okay, the integer solution. We're not solving the linear equations for any number. We have found an integer solution. So the theory, in number theory, we find out if now this theory, how to find the solution. First, you need to check, see if the solution actually exists. So the GCD between this must equal to 1. So then the method for the final solution, first check, see if the GCD of these two is equal to 1. So if it is, then they proceed. If it's not, you just claim that it doesn't have inverse. So this number, mod D or and mod that, so n equal to 1, is it possible? And if GCD between this and m, okay, is not 1, there will be no solution. So then you will have no solution. So first process is we apply a Euclidean algorithm to compute GCD. In fact, that algorithm is also half of the work to find the solution. We call it extended Euclidean algorithm. So let's first go over the GCD, uh, Euclidean algorithm to find the GCD. Let's first go over how do you find GCD, which the algorithm is actually half of the finding the inverse. So let's see, finding GCD of 84 Euclidean geometry. What the idea is that you keep on dividing this number, dividing the remainder into the divisor, and then until you get a remainder 0, and then you're done. Let's work out this problem. So you have 84 and 60. What's the GCD? You divide 84. So you divide 84 by 60. So 84 actually divides 60. The the quotient is 1. So you write like this: 60, the quotient, that's multiplication, times 1. And the remainder is actually 24. So, and then what do? You divide um, the remainder and into the divisor. So then you will say 60 divided by 24. Then you have 2. Okay, 24 times 2. And then this remainder is actually 12. Okay, you can work out this math. You're very good at it. So the remainder is, and then of course, remainder to divide divisor. And then next one, you divide 12 into this. So 24 divided by this equals to 12. Okay, and into 24, so that's 2. In this case, the remainder is 0. So then you're done. Once you see the remainder is 0, and done. So what is GCD? And GCD is nothing but this, 12. Okay, so now this is the GCD method. Whenever you have this, you're done. So now you just make your own example, try to practice, you will find it. So now what this has to do with inverse? Then let's have, if this is, in this case, 60 modulo 84, there is no inverse for 60 because the, they have GCD equal to 12. So now let's find an example that does have a solution, our previous example. So GCD of 480 and 17. So then let's do this one. GCD, another example, 480, which is above 17. So this example, so I'll have 17 and 480. So that one we know exists. We just pretend we don't know. So we divide 480 by 17. Then you get a 28. That's a quotient. And the remainder is 4. Okay, and so that's the remainder. And then you divide the remainder to this. So you have 17. So you divide this to that. 17 to into, so that you have 4. The divisor is 4, so the remainder is 1. So then I divide this to there, and then you will have 4. So that's the divisor, and then you have 4, and the remainder is 0. Then you're done. But in this case, actually, this is the above case. This is one of the homeworks. And then in this case, we do have an inverse. So we have inverse. So this is 1. So we have inverse. So inverse, yes, inverse exists. So that's the first half of finding the inverse, but it's none other than just find the check, see if, but this is already half of the work and find the inverse. Now we're going to work backwards. It's called a backwards or extended Euclidean algorithm to actually the uh, find out the inverse. So in this case, we find the inverse of 17. Modulo 480. So we find 17 inverse mod, of course, usually write like mod 480. It's possible. Now let's work on this in another slide. Continue. And so GCD is find out, it's 1. So now the procedure forward is to extend this algorithm to find the inverse of 17 modulo 480. The first step here is to rewrite this procedure, the calculation of GCD, into the remainder, simply arrangement, and you put remainder 4 and 480 divided by 17, that's the quotient, and that's simply linear equation, and then you do the game, turn the divisor, turn the remainder into divisor and divide into 17, then you get a remainder 1, 4 times 4, and this is GCD is equal to 1, and you get 0, the GCD is 1, that's quotient. So you read this on these columns are the remainders. So now you do it backward. Remember, we can try to find the equation of linear equation with one side is 1 equal to the 17 times the inverse minus a y, the number, and the times the modulo, the capital N. So what you do is actually you go and work backwards. So the forward step is to find the every time you go remainder into divisor and divisor into dividend and continue and until you get 0. But then you reverse this backwards, you plug in the remainder back into the divisor. So the first step in this is this. You're going to plug in this equation. So that's the remainder to the second equation here. You plug in there. And so that the other side is 1. And remember, 17 is the one that's first number we're given. We try to find the inverse of that under modulo 480. So in that case, let's plug that in. So then they continue here. So the 17 minus 4, and then times that 480 minus 28 times 17. We simply reorganize this a little bit. So remember, we put 17 is what we're interested in. That's the A here. So that means 17 plus 4 times 28 times 17 minus 4 times 480. And then you work out this 4 times as 112. and then put together is just 17, 112 plus 1, so 17 times 113, and minus 4 times 480. So now we put this into the format of the equation we want, right? So this is A equal to A, the number X minus plus Y times N. Obviously here A is 17. Okay, X, we actually find the inverse is X here is 113. Okay, and Y is negative 4. And our N, this given, is 480. So of course, this is the same problem. We find, so this answer is of the inverse is this. Same, okay? Actually, no doubt. So this is, of course, using this is much more tedious. If the number is complicated, you have multiple steps. Every time you keep on plugging, if it is one more step, you're going backwards, plugging from the second one, from the one that you start from second last one, and plug in this. And if you have more, you keep plugging more and more, you're going backwards, and you end up with equation like this. You recognize, remember, you recognize that this this part, so this is in this format, so that's equals 1. So that's how you, that's the algorithm. Let's work on a more sophisticated problem to familiarize you. You can make your own problem to exercise this. And of course, some of you are good programmers. Actually, most of you are. And you can look, this is the same algorithm, not in example, but in the code. Every general line you can write like this with the Euclidean procedure until you find the end of the remainder is 0, then you're done. Okay, whenever remainder is 0, you can recognize the GCD. Once GCD is 1, then you can reverse it to find out the inverse. Okay, let's work on a more sophisticated example. Okay, here is another example, a little more complicated, but exactly the same idea. So 23 inverse under modulo 101. So in other words, you want some number multiply with 23 and then mod 101 and get to 1. So once again, you do the forward Euclidean to find the GCD. So you divide the 23 into the 101, and that's the result. 4, that's the quotient, and that's 9 is the remainder. And once again, you use the remainder to divide into 23, and so on. So once again, you divide this remainder. So the remainder, so it's divisor, and then you divide this, and then you have then this one become the dividend. So it's like a repetition, recursion, okay, easily to make into a computer program. But here we use the actual example. So the divide, and then you remainder 5. And then you do the same, 5 divide into 9, and then that's remainder 4, and so on. And once you get to remainder 0, you're done with the GCD. So the GCD is 1. So which means this exists. So exist, then, so the inverse exists. Therefore, now extend this idea. So then starting point, you don't, it's reverse, your starting point is this. So you rewrite this equation into this one. So from second to last one, so this equation, this goes in here. So that's simply algebra. The remainder one, that's that one, ultimately one is here. And then this one, the second one, is rewrite into this 4. And then you obviously substitute this 4 into here. And then you get to this. You get this one. So you remember the number. So the dot simply means multiplication. Okay, and so then you remember the 5 is one of the remainders, basically reverse. But then next you will look for this one is here. You rewrite. Okay, and substitute this 5 into this 5 here. You reorganize it, recognize the 23 is what you are going to find the inverse of. So you organize your equation like this. So then the next one, this is the equation 1 equal this. And next one is you have 9 here. So this one is 9 is this one. Okay, rewrite the 9, remainder 9, you substitute into this 9 here. Okay, you reorganize, you have 101 and this. Okay, and then you rewrite this 9 into the above and reorganize, and then this is 9 over here, and then you, so that will yield this. So 1, okay, replace this 9 with this 101. You reorganize, there's another 101, so then you will have this. So this one is always 1 on the left. So here, and you reorganize, and then 101, -5, and then finally from here you have this last line. Now, so you see it's in the format of this equation we want to find out. Actually, that's actually the definition of the inverse. So recognize here, this is original A, that's the question, and what we find, the inverse is actually x, 29, and that is none other than our modular, and that's 5. But in other words, if you use my original algorithm, simply brute force search, you keep on doing the division and find an integer, and you will move 5 steps. And then, of course, this is more interesting, and so you can easily turn this into a computer program. In fact, there's a lot of computer programs online can calculate this inverse. It's not that hard. So hope this is helpful. Okay, just to practice, make it perfect. You just make yourself a couple of problems. Try to see if you can solve it. If you have a question, and we can talk about it during office hours. Thank you.